just for introduction. So I'm a research scientist at Valeo, and I'll begin a bit with what is Valeo, because it might be unknown to many of you. So Valeo is actually quite a big company working in the automotive industry. It's what's called in the typical jargon is a supplier. So essentially making all sorts of, making most of the things that are in the car except the car itself. So these things can range from headlamps, wipers, electric engines to sensors, which is the focus of my talk today. So across the years, Valeo has been present in the ADAS revolution, starting since the early 90s with the first ultrasonics sensors for parking, and then all adding up all sorts of functionalities that we have in the majority of the vehicles on the road nowadays. And we see that as we approach our current days, we ramp up our sensor stack with LiDAR and with all sorts of perception functions that are making our vehicles more and more autonomous. So as I said, currently we provide the sensors, but also the software and the perception solutions for autonomous parking, for safety and for assistant driving and general parking traffic, but with all the things that come around it. So the processing units, the cameras, the next generation sensors, but then the solutions and the validation that come with it. So in terms of scale, we make a lot of sensors, as I said. So in the past 30 years, we have produced about 1.5 billion, and in the next 5 years, we're forecasting that there will be a same amount of sensors deployed on all sorts of vehicles. As I said, it's not just for high-end vehicles, it's for all the vehicles that we have on the road. So to give you an idea of the type of sensor that we have, especially for ADAS, so we have the ultrasonics, which are very short range, near field radars and mid range radars, cameras, surround view cameras, which are fisheye, and the long range cameras, which are typically peephole and can be either in the front of the car, but also on the rear, and sometimes on the side. And of course, we have a range of LiDARs, out of which the Scala one is so far the only one that has been validated L3 on the European and Japanese roads. So based on these sensors, we foresee different configurations depending on the level of autonomy that we may have. Again, a thing that is specific to a supplier is that it's not always that you solve the entire sensor stack. So a car manufacturer like BMW or like Mercedes or like Ford may select just our cameras and the LiDAR for someone else, and the LiDAR for some other supplier. So we're always modulating a bit the architecture that we have to provide to our customers. And here we are, just inside the Valeo. So there's this Valeo team, which is the team that I'm working in. We're about 25 researchers and PhDs, and our scope is our objective is to do research, open research, publishing code and papers. Releasing all the reflections that we have upstream in the future of ADAS. So we have several collaborations with different labs in Europe and institutes. We have 2 offices, one in Paris and then one in Prague. And in terms of topics, well, we're moving to some extent with the community, so topics change across the years, but as main target, we always deal with perceptions, with data efficiency, so perception the camera, LiDAR, multi-camera, radar. We deal with data efficiency, self-supervised learning, annotation efficient learning, active learning, these types of things, but also driving, forecasting, reliability, and explainability of our models. So we can find more info on our website where we have most of our papers released. So coming back to the topic of today of foundation models in the industry, so we look at them as models that we train once and we use several times. I will not remind, I saw that already Sergey reminded a bit the definition that we have of foundation models in Ramasani et al. But essentially it amounts to that, finding a way of training the big model on a lot of data without much supervision, and then we use it as much as possible. So my background is also a bit in self-supervised learning. So whenever I do foundation models, I remember the pipeline from self-supervised learning. And there you usually have 2 stages. So you have one stage of pre-training. So you pre-train with your network on a prefix task that does not have human labels. So here I'm giving one of the early examples that we have, which is rotation prediction. And this is a paper from my colleague Spiros Gidaris. And it's really simple. It's just to illustrate you need a very simple dumb task for which you can extract automatically the label. you train the network for enough of time on a lot of data, and then in the second stage, you take your network at data and you fine tune it for whatever task of interest you may have with your LiDAR. So in general, today I'll be following a lot this type of philosophy of two-stage, and you'll see a bit how we can offer some solutions for the first stage and for the second stage of the training. But before going into that, so why would it be a good idea to do self-supervised learning, especially in our case when we are dealing with driving data, urban data. So first, the data is enormous. So with self-supervised learning, we leverage large amounts of unlabeled data. We saw that scale it matters more and more. So we have ChatGPT and friends showing it us. But also there are some specific cases to driving. Like sometimes annotation is difficult or expensive, and in other cases, like we saw with Raj before, for dense depth estimation, it's really difficult to obtain it, to annotate it by a human. So you need again self-supervised learning. And finally, and this is again something specific with people launching things in production, is that training data sets in the world are evolving continuously. And to show a bit my point, so here it's the evolution of men's fashion from the 80s to in the 80s in general. So we can see that the data distribution shifts all the time. So there's different fashion trends, different colors. So it's impossible to annotate at all times in one them, but there's a change in the world to go back to the dashboard to annotate even more data. So to bring some examples from what we have in Valeo, so we see a bit of a similar pattern. Right? So we are doing cameras since 30 years now. And at every new generation, we essentially almost double the number of pixels, and we have a new sensor. So what we do, we have a new contract, a new company. We do acquisitions again. We have to label again. So these sensor specs are changing all the time. Same for LiDAR, same for radar, and same for all the sensors as we are progressing. And to prove you the point with something more specific, so I here have a map of the evolution of headlamps. So this might not be obvious. So actually the headlamps, there was quite a bit of revolution and they're changing also continuously. So we had regular car lamps before, then we moved to halogens and to xenons, and then with LED, and now we have a laser light. So these are getting increasingly sharper, but actually they generate different data distributions. So here I'm comparing halogen versus LED. So you can see that it gives a different distribution of the images that I have. And then again, I have to annotate again, or to take into consideration that there are cars with these types of headlamps. So, and another thing of why self-supervised learning would be a good idea is that now in the past years, in the advent of different foundation models, be it just simple vision, but also VLMs, visual language models, and even LLMs, we see a lot of use cases for the second stage that appear. So it's not just fine-tuning on some labels. We can do actually a lot of things. On few levels, we can do actually a lot of things with our pre-trained models. So one, in this case here in RangeVid, it's a method for LiDAR perception. Since it's a transformer, we pre-trained the transformer for images, and we use exactly the same architecture for LiDAR. We just adjusted the input and the output, and it works pretty well, and it improves performance against comparing from scratch by leveraging just the information from images. We can use these models for unsupervised segmentation. So here we learn to discover pedestrians, cars, all these classes, thanks to the help of LiDAR and so by having just the input, the image as the input. Here we use dyno features for active learning on point clouds. So we have pairs of images and LiDARs, and we can project the LiDARs into the image space, extract their dyno features, and then find the most relevant ones that I want to label. And we can see that in the very low data regime, our method is in red. With 1% of the label points, this leads to dramatic improvements compared to the typical active learning strategies like course sets, entropy, and all sorts of uncertainty. And the last two, I'll be covering them into more detail, but they amount to ways of distilling one model into the other, one model from one modality into another with quite good results. So what I propose as vision and what we see in terms of how to approach things. So you saw the North Star that Alex made this morning about embodied and end-to-end driving. And I adhere to that. I concur to that. But by seeing a bit what happens in the whole industry and the amount of clients and the architectures and the solutions that we have, that each client has a certain setup, a certain chip, a certain constraints in flow. So it's very heterogeneous. The way we see it is that, well, we want a modular pre-training. So we want to pre-train our image encoder in a self-supervised manner because it has some sense of specific data and some specific pairs of data. And then if you want to do bird eye view, we pre-train also this bird eye view projector. Similarly for the LiDAR and for other sensors, we can find ways to pre-train them on large amounts of data. And then when they're ready, we can bundle them together and continue training towards an embodied or an end-to-end pipeline to address different tasks that might be downstreams in the surround of the vehicles, be it forecasting or different perception modules. So in the talk today, I will do a focus on these three areas, and I will start with the image encoder. So as I said before, in foundation model, we want one model trained for a long time to be used for all. So in the language, So in the field of the imaging or self-supervised learning for images, so our team, well, there's so much activity there in finding different strategies for self-supervised training of image encoders. By using contrastive learning, by using feature reconstructions, by using Dino, so by math autoencoder. So there's a lot. We have worked as well on that, and the focus was always not necessarily to train on ImageNet and to have good performances on ImageNet, but also to see, having a mindset, a bias to a prior towards having good performances downstream on complex tasks like detection and semantic segmentation, or to enable few-shot adaptation. The thing is that they work really well on ImageNet because it's balanced, it's a nice data set, so we pretend to do self-supervised learning on a Lego data set, but this is a very curated data set. So when we go to driving scenes, so I'm here, I'm showing side-by-side some images, randomly sampled or almost randomly from ImageNet and on the right-hand side for BDD, 100K. So you can see there's some starkly differences. In ImageNet, you always have an object is centered. Usually, on street, you have sometimes an empty street, a few cars, a lot of empty space. Let's move on. Again, some objects of interest here. Well, we have, again, some road, a few cars somewhere in the back. And again, yes, well, now this car is closed, or some pedestrians. Never one object like we have in the internet, where it's easy to identify that there's a main object dominating the scene, so you can devise differently your self-supervised training strategies. And I can go on and on and get at the point of the difference between the two. So actually, most approaches struggle to pre-train just on driving data compared to ImageNet. So there's some tentatives out there, but in general, I would say it's a bit of a wasteland. There's not so much thing happening here, interesting there on having a self-supervised strategy just for events. Because the data is boring if you compare it to ImageNet. There's not much happening there. So this has been the case for a while. The emergence of these new foundation models like Dino, V1, V2, and Clip have rechanged a bit the focus of pre-training image encoders. So there's two ways of reusing them right now. So one is to have the pipelines that we have, these teacher-student pipelines that we have in the self-supervised learning, but using as a teacher one of these models. So you don't start from scratch, you start from Dino, you start from Clip, and then you have your driving data, and you are doing a lot better because these models have seen a lot, like really a lot compared to what you see in driving scenes. So in driving scenes, you get a lot of information, and that's useful, but you will never get the diversity and the amount of things you can find either on the internet or on other data sources. So we want to couple those and to use them together in such a pipeline. Then, if I look at the ways of using the other ways of using these models, we can fine tune them. Now, since they're so big, we don't need to fine tune them completely. We can actually freeze them or just train a subset of the parameters. Since most of them are now vision transformers, we can do what is called visual prompt learning, or learning just for adapters to learn just a part of the network to fine tune it for certain classes of interest. And here I'm showing an example from a recent paper from CVPR, where they look at the generalization of semantic segmentation models across different data sets by training just on one. And we see that whenever I'm using a clip or a dyno V2, in particular dyno V2 is really strong for such systems. So they are to be used there in the they have used that. So in another axis of the study, so this might be less known. So because you have, well, I think it's in the spotlight. The self-supervised learning on images is quite known. But another thing that we have been studying in the team is self-supervised learning for LiDAR. Essentially, we keep the same same setup as before. Stage 1 pre-training, stage 2 on pre-training on auxiliary task, pre-text task. Stage 2 remove this auxiliary task and fine-tune our task of interest. So one of our early works on doing that is called Also. It was published as last CVPR, and there we want to pre-train a LiDAR network by using a supervision surface reconstruction. So we assume that if we are managing to reconstruct the entire scene based on these sparse points on the point cloud, we have some understanding of the scene and the relationship between these points. So I'm not going into much details, but the idea is that while I have a point level point cloud network, it produces some point level features, and then I query from them. I take some representations from them to decide whether a certain location in my scene is occupied or not. And this can be done quite straightforwardly by using the layout of the scene, so we know which space is free, which space is occupied. So whenever we touch on a surface, we ask to reconstruct the neighborhood, and we use this as supervision for our LiDAR network. And when we evaluated we evaluate purposely on few-shot regimes to show the benefit of actually learning something with the network. So when we evaluate be it on new scenes or on semantics kitty with 1% of training data, we always see boosts with respect to the previous methods that we're trying to do self-supervised pre-training on for LiDAR data. In particular, we have point contrast, which is the dominant method, but for indoor point clouds, and in-depth contrast, which was one the first one that we did it for outdoor LiDAR, which is sparse and it has its own peculiarities. In other settings, we looked at other approaches to simplify further these pre-training strategies. Because before we had these point contrast methods, contrasted methods at the level of the points, where you want to compare one point against all the others in the scene. But they are pretty brittle because you might consider, so you have one point and you consider different augmentations of itself as positives and the other negatives, but the other points might be lying on the same object, so this can introduce some noise. So to deal with that, we have a simplification here. We just squash the points in the bird-eye view space. We define a grid, and we consider that all the points belonging to the same bird-eye view self in this grid are positives at different moments in time. So we do scans at different moments in time, and we compare the bird-eye view features at the same location after the warping. So we consider these two as positives and the other ones as negatives, and we apply a contrastive learning approach. And this works quite well. It's more stable than the previous approaches in contrastive learning. And similarly, over the board, be 0.1% of the labels, 1% of the labels, 10%, we always see an improvement with respect to previous methods without pre-training or with a different pre-training structure. So with this, I'm concluding the first part of the talk, where I was speaking essentially of single models, be it for LiDAR, be it for camera. Another thing that we see emerging, and that we have it's a specific of autonomous driving data, is that you have different sensors that come in. Different sensors of the same type. It's a multi-camera setup with different cameras mounted on the vehicle, but also different types like LiDAR, radar, and so forth. So in the next, I will take a highlight on two types of models that allow multi-modal training. So the first one is techniques that enable LiDAR to supervise image models. So just to make it easier, so whenever I have here, I'm dealing with an image model. So whenever I have the other one with the car and the LiDAR, it's a LiDAR model, because the visualizations can be quite similar. So the first one is a method that we call POP3D, which was our take on doing 3D occupancy prediction in an open vocabulary manner. So we have as input here just the surround view images, the images from new scenes, and what we want from that is, without human supervision, to get an occupancy map in the 3D, but also with open vocabulary properties. And why is this interesting? Is because that it allows us in offline mode to do zero-shot semantic occupancy segmentation. So it allows us to discover new classes that we might not have thought in the initial annotation campaign. Because if I want to detect a new class that the client has, then I have to go back to my data and re-annotate. And annotated LiDAR is pretty expensive. And then I can also do retrieval. So since my network is producing 3D features that are open vocabulary like clip, I can query with text query. So here I'm just saying black hatchback, and it identifies in this 3D space the voxels that correspond to this hatchback. I've already mentioned some of the motivations. We have a lot of weird things happening in the world, and it's difficult to come back to our LiDAR to re-annotate it point by point, and it costs a lot. And again, my LiDAR changes, I start over. So how does it work with our method POP3D? So we, as I said, we want to do open vocabulary 3D semantic occupancy prediction. We just have a training some unlabeled image LiDAR pairs and the pre-trained image language model, so clip. At inference, we just have the images and the text queries of what we want to find in our 3D scene. So here in an example of I have an example of text-driven retrieval. So the pipeline is pretty simple. So for those familiar, we are using we are moving from the camera space to the 3D volume space with something resembling TP deformer. People might be familiar with that. So we go by using the information from the camera extrinsic and intrinsic, we project them into this 3D volume, and we end up with this 3D grid. And then once we are here, for each voxel, we plug in two MLP heads, which need to predict, the G head needs to predict whether the voxel is occupied or not, whether there's a surface there or not, and the H head needs to produce clip features for in this space. And in terms of supervision, how do we do that? We have two losses. So in the occupancy head, it's easy since we have the LiDAR, we can generate, we project the level, we can voxelize the LiDAR space, and with a given granularity of our space, I can decide whether a voxel is occupied or not. It's occupied if it has a LiDAR point in there. It's unoccupied if not. And I have a simple loss for the frequency. It's typically used in segmentation, the low-pass and the cross-entropy losses. Going on for the 3D language head, again, it's in a similar approach. We take advantage of a pre-trained visual language model, clip, then the other. We densify those, and we get the features at the last convolutional layer, or at the last layer before the projection into 3D. We project the point clouds into this space, so we have them aligned, and each point will have this corresponding feature. And then my head needs to predict for each voxel, needs to predict the corresponding features at the places where in the image where the point clouds were projected. And doing this without human labels for a decent amount of time, so we train the new scenes. In this case, I think I forgot to mention. So this part here is just for training. Right? So this part here, and I'm not changing my visual language model. Right? I just learned to imitate these visual features. So when we look a bit at the results, we compare with methods that are supervised. So here, this is a benchmark introduced into CVPR24, where you generate this volume of semantics. But you use the LiDAR information just because it's segmented, and you use just it's a tweaking of the LiDAR semantic segmentation benchmark, and you essentially see in which wherever you have a voxel, the point cloud falling in a voxel, you look at the class and look at the prediction of this model in the 3D space, then evaluate it like in semantic segmentation manner. So starting from a mass clip, this is a model for doing semantic segmentation, where we project them in the LiDAR point cloud. So we get like 23% MIU, but this is a bit cheating because we know where to project in the LiDAR. Our method that does not use any LiDAR at runtime, it gets into 0.26. So this is in zero stops, right? So we just give it the text queries that we want to have. And when we compare with methods that have exactly the class level information and are trained for these classes, we see that we're actually not that far from them. Another interesting finding is that when we look at actual occupancy, it's thank you. Okay, thank you. So another thing that we looked at is on occupancy. So here we do it in a class agnostic manner, comparing with the supervised method, it's deciding whether, well, predicting whether a certain voxel is occupied or not. So interestingly, here we're actually better than the method that was trained in a supervised manner. Like having access to semantics that was trained to predict exactly the classes and the location. So in purely occupancy, we're better than that. When we go to actually comparing the classes, so this is the MIU, we're lower, but we're in zero shot. Right? So it's, well, it's not a great performance, but it behaves differently. Well, it performs differently compared to the supervised version. And another task that we looked at is retrieval. So we annotated a small data set of voxels, and there we essentially annotated with some classes, and we did a nearest neighbor classifier, taking a certain voxel, a query voxel, and looking across the data set where these voxels corresponding to this object. With the ones with the example with the black hatchback, that we have quite a few classes annotated specifically for this task of retrieving the voxel that corresponds to this class in the data set. So some cherry-picked results on what we get. Again, this is what we have as input, just the cameras. We predict this surface in the 3D space, and these are the text queries that we apply in a zero-shot manner in the on each voxel. And the results look relatively nice. Of course, it's not the supervised thing. It's just the thing that gets you to mine some patterns that are unknown in your data set to retrieve whether you have something of your interest in the data set. And similarly here, we discovered this bus here. So this is another scene from new scene. And you can see that it identifies some voxels belonging to the bus. So again, Clip was trained to see buses, but it was not to be trained to predict features in the 3D space. And in there it recognizes this bus. And same from the retrieval benchmark, the black hatchback has shown it to you before. And I have another interesting one here, stairs. So again, this is not an annotation in new scenes. It gets to fire to identify it on to some extent. So here, blue is lower similarity, red is higher similarity with this text query stairs. And another way of using, kind of related to that. So POP3D is to be used mostly for offline, but we come back and revisit the idea of self-supervised pre-training. So this is a work that was the read group that we presented today at the WEB workshop. We want to pre-train a network for bird eye view perception. So here we don't do a 3D volume from the beginning. So we are having the typical bird eye view pipeline, be it lift, splat, shoot, simple depth, form, or whatever you want, and we add this auxiliary head, which predicts again the occupancy in this volume. So here in the bird eye view space, we have lost the height information, and we recovered here with unsplatting, and then we have a similar approach of attaching a linear head on top of each voxel to predict whether it's occupied or not from the LiDAR. And in this case, we use Dino V2 features. We want to imitate Dino in this space, and then in the second stage, we completely remove this yellow part, and we fine-tune for 1% of the label data. So we can see that this is the image that we're training in yellow. I'm showing here two architectures, simple depth and deformer, on vehicle segmentation and not segmentation. And we see that on 1% of the labels, we always get boost with the occupancy. And whenever we add also the Dino, we get even further. And what's interesting is that when we look at these benchmarks like new scenes where you simulate the distribution shift, you actually have you see that across different corruptions, so we jitter. So you have all sorts of corruptions like adding fog, adding motion blur in the input images to see how is your model behaving in conditions it has not seen. So we can see that our model in green is better than without the model that does not have that better thing. So as I said, there's a second model that I wanted to show you today. It's image to LiDAR. So this is related to a paper that we're presenting right now at, in the main session, in the main track at CVPR. So here we are looking at ways of distilling a pre-trained image model into LiDAR, into a LiDAR model. So I want to train my LiDAR model to imitate whatever my foundation model on the image side is predicting on the line images. So previously, the state of the art had a relatively complex approach where you essentially have an image, a point cloud encoder, an image encoder. You do a segmentation of all you do a super pixel segmentation of the points of the pixels in the image space, and you group when you project the points in the image space. You want to group these points together. Pixels about points that fall in the same segment of the image space are considered positive. The others are considered negative. And this was state of the art at the time when we released the paper, but it was a very complex approach. Nothing politics is also our pixel. I'm not bashing that percent. So the state of the art at that time with these types of features, I mean, this in essence it's a very simple setting. Just the architecture ended up more complex, but it's a really easy thing. You want to distill an image model into a LiDAR model, and it works pretty well. However, at the time, when we look at the gap between a fully supervised model on semantic segmentation and all the models that were pre-trained on the same data set but with a linear flow, we have a gap of 33 points. With the method that I will present you in a minute, we managed to narrow this gap to 10 points. I remind you, we pre-trained the network and we just fine-tuned the last layer, linear flow, and we compare with the model that was trained on the entire data set with full supervision. So we are still not there. We still have 10 points, but we are narrowing the gap. So just to tell you how we tiered apart the original approach that was state of the art at that time. So we simplified dramatically. So this is a paper by my colleague Gilles, where he and the colleagues proposed a dramatic simplification of the pipeline that I've shown you just before. So before we were using 6 cameras as the new seeds and the full LiDAR cloud, the surround view 360. A simple thing that we started with was actually to do 1 camera at once. So this simplifies your data loader. You don't need to load 6 images to have the point cloud in mind, and it reduces quite a bit the memory load. Another simplification that we did, it was this linear head on top of of the image encoder, and we added here this initially to reduce the dimensionality because we have big resonance at that time. They have 148 2000 dimensional features for a point cloud is quite a lot. So we had to reduce those with a linear head. The downside is that actually per term we didn't have access to the actual 2D features that were learned by this model. So we removed that, and then we looked a bit at the contrastive loss. It's complicated. You need to keep negatives in mind. You need not to match positives with positives and so forth. So we removed that and we replaced it with a simple cosine linearity loss. So we essentially want to align the features of a point cloud with the features of the pixel in the place where the point cloud falls in the image space. So that's it. And when we look at the impact of all these simplifications, so here we have 2 architectures for point clouds, MeQNet in waffle iron. So this is the baseline where we have well, this is the reference of one point memory in time. So we will be looking in relative with respect to that. So as we remove the 2D head, we can see that we get an improvement immediately, right? So we remove this 2D head while still keeping your contrastive loss. So in the next step, we remove the contrastive loss and we do a cosine similarity. And again, the performance improved further, a bit less on MeQNet, but quite significant on waffle iron. And finally, you see here, I have the number of camera images. When I remove, for the MeQNet, when I remove the number of cameras and use just one view, I gain quite a bit in time and memory, really a lot, by losing a bit of the performance. But I can train for longer if I want to achieve that level of data. So when we study the influence of these 3 pillars, we have 3 pillars that we study based on the modifications that we made. So the choice of in the scale of the 2D network, the scale of the 3D network that we want to train, and also the mix of data. So what we noticed is that when the choice of the scale of the network and the 2D network actually are quite important. So we looked at different teacher models. They're all pre-trained on images in a self-supervised manner. So the first one is MAE, then we go with Dino V2, Dino V2 bit base, and Dino V2 large. So as we go to more recent models, sorry for that. Yes, installation. It was related to me. We were here. Sorry for that. Well, the idea here is that the bigger the teacher model, the better. So this was not a factor that was studied before, and well, all the findings that we have are pretty simple and ready to use. In fact, so I will not spend too much time on them. But similarly, for the scale of the 3D network, so the one that we actually pre-trained, we looked at different sizes. So we looked at this waffle iron architecture, for which you can control the width between 96 to 768 dimensions. So the green one is trained with a small teacher, a bit S, and the blue one with a bit large. And again, we see very obvious improvements across with bigger scale and bigger features. And then finally, we looked at the impact of the training data set. So what we did, we gathered all the data sets on LiDAR that we have available, new scenes, MTD, semantic TD, Panda 64 and Panda GT. We made a data set, and we first pre-trained on each individual one, and then fine-tuned on the other ones. We can see that, well, when we pre-train and fine-tune on the same data set, it works well, but then when you go on another data set, for example, see, I pre-train on new scenes, it works well, but when I fine-tune on semantic TD, the performance is relatively low with respect to its original data set. But when I pre-train on all these data sets and then fine-tune on a specific data set, we can see improvements quite well. So this generalizes across architectures and settings in our work. So in general, with optimizing these three pillars, we've seen that we got improvements over the board, be it in linear probing, the fine-tuning of 1% of the labels, and new scenes on semantic TD. I will skip a bit the qualitative results. So just to conclude, so what we notice is that scalable and simple pre-training strategies were long known to help a lot in the mainstream image classification, image-based settings, but we see that they're becoming first-class citizens also in driving data. If we have data outside of the autonomous driving domain, it's really helpful. It can be internet, robotics, whatever. You really want to have this intelligence and this richness of of data that you have seen outside of the roads. But if you want to go to generalize to outer distribution and to have robust features, it's not enough to have just a driving data. So if we train on different datasets and camera configurations, we get promising results. So I highlighted here Scalar, which was trained on different LiDAR datasets, but we have another work on trajectory, on motion forecasting, where we assembled all the datasets existing there and trained the foundation model on all this composite data. And again, it improves things, and you will see. And we tested it in the Argoverse 2 end-to-end forecasting challenge. We use both Scalar and Unitraj. So what we did is the approach that I was mentioning before. We had a modular pre-training, so we pre-trained all the modules on trajectory forecasting on Scalar. So in the case of Scalar, actually, we just added the Scalar features without any fine-tuning on this Argoverse data, and it led to a significant improvement of the forecasting properties with respect to the previous works in the one last year. So we were 13 points above the previous methods for forecasting, to stress on the importance of the pre-training, whether your pipeline is empty or to give some perspectives. So what we see, and we saw also today, so there's different forms of world models that are taking over right now. There's different tastes with different flavors. According they're all interesting, and they're all paving the path towards so what we see here, and I appreciate especially you guys for releasing some data sets in the community. So we have the Open Drive YouTube data set, which is 1,700 hours. Right. So all the public data sets that we have so far were like 300 hours. Also, New Plan is a nice data set, but it's just 100 hours. It has calibration, it has LiDAR, it's really nice. While the Open Drive YouTube is 1,700 hours of non-calculated data, but it's really useful. So what we need is a lot more. The Gaia 1 has at least 5,000 hours. And I think they will have even more. And there's really a need to run more open research in this field. It's nice to see the nice models and their performances, but if you cannot touch them, if you cannot collaborate together or work with them towards improving them, it's a bit of a missed opportunity. So we really need to do that. We're doing our part, releasing everything there, what we do, and we hope that others will do. I think that I forgot to mention is that there will be even more downstream cases, stage 2, that I was showing before, here in the new generation of foundation model.
Thank you very much, Andrei. Are there any questions from the audience to the speaker? Yes, please.
So already, it's to get back to the slide. So, in contrastive learning, you have a lot of moving variables, like the number of negatives, and something that we did, because in these settings, because it's quite difficult otherwise to scale, is that the negatives are from the same scene. So and you won't often end up by contrasting pixels, points from the same object. It can be the car, or you have points landing on the same car. So since they're in the same scene, you end up contrasting. Or if you have multiple cars in the scene, you don't have any way of doing that. So this ends up confusing your model, and it also is more unstable and trades for longer. While just aligning one point with itself, you don't care about the others, and it's much simpler. So you don't need to have a bunch of negatives.
So I have a question. So regarding the design,
Yeah.
It's very common where like you visit the application some conference value or have some dimension of that.
Yeah. So this issue of motion, like feature collapse, arises usually indeed in methods that do cosine similarity, but it's methods that have a teacher-student architecture, right? So you have, but the teacher is an exponential moving average of the student. So we end up predicting the same thing. Why we are not vulnerable to that is that at the input of our teacher, I have images, while at the input, and they are always changing because I have a Dino V2 or I have, so that thing I know it produces all the time good features, and they're not the same all across the images. And on the LiDAR part, I train to imitate that, right? So I train to imitate Dino or Flip or whatever. So I don't have this risk of feature collapse. Usually you have this when you give the same input to the two models.
Maybe I have a question. So you showed a lot of nice results with LiDAR point clouds versus images, but we see this dichotomy between the representation spaces for these modalities. And so what is like your take about like the actual space that we need to use for driving scenes for our presentations or for our outputs, for example? You showed also some occupancy results.
That's a good question. So in terms of alignment, we have some experiments on scalar, but we didn't show them here. So actually you can distill even a clip into scalar, into LiDAR, so we get open vocabulary LiDAR features, right? So we have the same things that I was showing you on POP3D, we can use it on the LiDARs to query by text. So you can align these features with sufficient supervision. I think the alignment that we want really depends on the end task. So if you're speaking in bird eye view, then again it's easy. I was showing you the modular pipeline, and then it's really convenient in bird eye view to do a la web fusion to align them, because then it will be helpful for downstream if you do 3D detection or if you do forecasting. The same actually applies even if you want to train an image encoder. A front cam encoder. So there are some data sets. For example, if I look at the Pandar GT, so Pandar GT, it's a data set that, it's a LiDAR that looks exactly like a front cam. It has a narrow point of view. And actually, even our LiDAR at Valeo, it's the Scala LiDAR has this type of camera-like look.
Yeah.
So then you can align them in this space. It could be bird eye view. It could be. So my take is that we can align them quite well. It's helpful if it's in the 3D world in a space that is common for them, but it also depends on what you want to do downstream.
Yeah. Thank you. I think, do we skip the coffee break, or because I think we are a bit behind time? Okay, so then we'll just take like a couple of final questions from the audience, perhaps, to Andrei. Otherwise, we can directly move to our next speaker. Okay, so let's thank Andrei again. Okay. Okay. So yeah, well, maybe we can have a short break if somebody wants to